All right, good morning, class. Yeah, just like I mentioned a moment ago, today we are going to continue on with the principles of gas metal arc welding. We left off at modes of transfer. We've gone through short circuit, and we're going to move into globular transfer today. So we're going to talk about that. What I'm going to do is I'm going to share my screen, and we're going to work through the slides in the PowerPoint together. Let's close this up and we will present this. Might take me a moment just to flip to slides, but there, globular transfer, just like that. All right, so globular transfer is our second mode of transfer. We have three modes of transfer when it comes to gas metal arc welding. First is the most common, that is short circuit. That's generally what we use in the shop here. And then our next mode of transfer is globular. So we're going to start talking about that. Globular transfer is generally avoided in gas metal arc welding due to problems with spatter. Some gases can help out with spatter. The C25 gas we use is pretty good at controlling spatter, but stuff like straight CO2 and then globular transfer can leave you with a pretty ugly weld. We don't want that. So we generally try and avoid using this mode of transfer just for aesthetic purposes. And if you are delivering a product to a customer, you want that product to look good. You don't want to have spatter all over that. So in some processes like flux core, that is solely what we use. Flux core is all globular transfer, but it avoids things like spatter by using the flux. The flux does a neat job kind of containing the spatter and bringing it back and basically reintroducing that spatter into the weld, and the spatter becomes part of the weld. It's quite a neat process. We'll get into that in the 20 level. I may do some demos and show you. I may show you just for fun when you guys get back as well. Basically with this, globules of metal are transferred through the arc of molten metal. So if we can imagine that electrical fan and it shoots globs of metal across the arc. If you've ever thrown a water balloon and you watch it tumble through the air, or you watch one of those videos where they throw a water balloon in slow motion and it's tumbling end over end and it's stretching inside the balloon, that's what those globs of steel look like in the arc. It's pretty neat if you can get a slow motion, high definition video of it. There's a few on the internet. I'll have to dig one up. Some 4K stuff. It shows that metal twisting and pulling and tumbling end over end across the arc as it transfers to the steel. It's pretty neat. This form of transfer is what we use for stick welding. So when we get to stick welding is all gas or globular transfer. Pretty neat. So it works well for some processes and not for others. Definitely gas metal arc welding, not ideal. Flux core, that's basically what flux core is. Same with stick. So third type of transfer, spray transfer. I'm just going to make sure I didn't miss it. No. Okay, spray transfer. This is the cool stuff. Basically what we do is we use argon gas at a minimum of 85%, and this helps basically ionize the steel particles. Instead of globular transfer, those big globs, each of those globs is broken down into hundreds of small little droplets. And we shoot a fine mist, almost like a fog of steel across the arc. And this adheres to the plate. It's very smooth. There's no spatter. It sounds really nice. It's got a nice kind of humming sound to it. The one downside though, you have to run high voltage for this. So it is only applicable to heavier steels. You cannot run spray on smaller stuff or you will burn right through. The amount of heat you run with spray transfer is quite a bit. So you have to be careful when using spray transfer. We don't generally use it in the shop here. I'm going to bring in a bottle of 85% argon for doing spray transfer, and that's going to be for demo purposes. So I'll show you guys that at some point when I bring it into the shop. I'm just going to grab my headphones here and make sure that I've got the ability for you guys to hear everything. All right, this should be a little bit better, hopefully anyways. So spray transfer is pretty awesome. Like I said, we use 85% argon. Now it's going to be a bi or a tri mix of gas. It'll have 2 or 3 different gases in there. But the argon is the most important thing. Without 85% argon, you're not getting that ionization of the steel across the arc. So no 85% argon, no spray. Voltage for spray transfer is higher, definitely. The 035 wire, it would be about 26 volts in comparison to 17 to 20 for short circuit. And then globular is in that 20.5 to 25.5 range. So there's different ranges for each of the transfer methods. So as we increase voltage, we work through the different methods of transfer. Small droplets of liquid metal are transferred through the arc. That's basically what I said. It's a fine spray, mist, or a fog of steel going across that arc. The arc is smooth. It's got a humming sound, very little spatter, super nice. What you're going to notice is when you're welding short circuit, your MIG gun's gonna have feedback because that short circuit steel comes down, touches the puddle, and then it pinches off. So you have physical contact with that puddle time and time and time again. So when you get to spray and globular, it feels different because that gun is no longer making contact with the puddle. It's shooting bits across the arc. So it's going to feel different, feel a little more smooth. Spray set up really nicely is just beautiful. Usually spray transfer is only used in flat and horizontal positions. So this gets back to that heat thing I was talking about. It's a hot process. You run in 26 plus volts, a lot of wire. So you are using this in positions you can control. So that's generally flat and horizontal. You don't want to fight gravity with this. Uphill spray is going to be a nightmare. Same with overhead. That's just asking for a bad time. So we use this in positions that we can control. That way we basically end up with a really nice looking weld that is strong, it's hot, it's everything we want in a weld. If we are going vertical or overhead, we're going to change our method of transfer. We're probably going to drop down to short circuit. It's much easier to control short circuit in the vertical and overhead positions. But nice thing is you guys don't have to worry about overhead positions. We don't teach that in school here. In the 20 and 30 levels, we do get into vertical, but that's a year away still. So this generally works. And so does this one, but it's not working. So we're going to move past these. Basically, what it was showing was the one was showing different methods of transfer across the arc and how it sounds when you go through the different ranges. But got some examples up here. So this is an animation of short circuit because what we have is the steel coming down, being pinched off, basically retracting, coming down, forming short circuiting in the puddle again. This one on the left here on the bottom is going to be globular transfer. We see that bigger dot of steel coming across the arc. And on the right is our spray transfer. These are just rough animations, give you an idea of the processes. Obviously not to scale, but quite neat. And as long as you know how to use them and how to properly work with these different modes of transfer, they'll be awesome. They're great. So stubbing versus arc hunting. This is going to be an interesting little bit here. So stubbing and arc hunting are two things that we want to avoid while working with a gas metal arc welder. Now they can be caused by different reasons, and some of those reasons are going to be we got too much wire, too little wire, too much voltage, too little voltage. There's two ways to solve every one of these problems. So arc hunting is what happens when the wire is going too slow. So you've got a lot of voltage, a wire comes down slow to your plate, and then it touches your plate and it burns way back. And then it's got to come all the way down, pinch off, and it burns way back. It's basically short circuit welding in slow motion. That's an easy way to describe it. It doesn't sound very good. It's kind of got a bit of a hiss or a wispy sound to it. A lot of electrical fan going on, and you're going to basically use the arc is going to melt the end of that wire before it gets to the puddle and makes that short circuit. So you're gonna have a big glob of steel hanging off the end of the wire as it's coming down towards the puddle. Definitely not ideal and not good. Couple of ways to fix that though. You can turn your voltage down, or you can turn your wire speed up. Both are gonna have a similar effect. So it all depends on what type of weld and what size weld you want to go onto the plate. So this may be from too slow of a wire feed speed, just went over that, dirty liner, loose wire drive rolls, or a compromised contact tip. So you're not pushing that wire out the end of the gun as fast as you want. Stubbing is either from, okay, well, now we're talking about stubbing. Stubbing is either from too fast of a wire speed or too low of a voltage setting. So stubbing is the exact opposite of arc hunting. You've got too much wire coming out too fast and not enough voltage to burn it off. So that wire is coming in and crashing into that weld puddle, and it's popping and it's busting off chunks of wire. It doesn't even get to melt the wire. What happens is that wire comes down, it hits, it rolls over, and then short circuits. That piece is going to pop off. That'll land in your weld, beside your weld, and you got little chunks of wire all over your plate. It's just not very good at all. It sounds terrible. It feels terrible in the gun because you're sitting there, you're holding it, you go to weld, and it just feels, well, you hear a pop, 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 and you can physically feel it in the gun, that wire hitting the plate. So to take care of that, we can turn the wire feed speed down if we're looking for a smaller weld, or if we need that wire feed speed to get the weld size we want, we have to turn our voltage up to match that wire. Every voltage or wire feed setting, we're going to increase the voltage to match it. There's a parallel or a kind of a happy zone for every one of the settings for wire. And basically, it's our job to kind of recognize these problems and then adjust our settings accordingly. So this is something I kind of assess you on in class when I see you guys. Sometimes I don't often do it. I'll just, tweak a machine before class. I'll kind of set it out of range, and I'll see if you can identify that and get it back to where it needs to be. And that's part of the problem solving process. And that just kind of demonstrates that you understand stubbing or arc hunting. And I don't do it often though. I'll often just do a demo in class. I'll say, hey, this is arc hunting, this is stubbing, and I'll grab a welder and I'll crank up the wire feed speed way over the voltage so that there's a big imbalance between the two. And then I'll just let that wire smash off the plate and show you guys that. Then I'll do the opposite. I'll do the wire speed way down or the voltage way up, and it'll burn that back almost to the tip. Hopefully we don't mess up a tip while doing that. So power sources for gas metal arc welding starts to get a little technical here. So welding power sources are constructed to meet specs are set by NEMA. So NEMA is the National Electrical Manufacturers Association. So we talk about CSA in Canada, how they govern our safety. NEMA basically governs the Electrical Manufacturers Association, making sure that every electrical manufacturer is working up to a certain code that they set. This code guarantees our safety and that the products are going to be safe to sell to consumers. A duty cycle on a machine. So this is something that is quite interesting. A duty cycle on a machine is how many minutes out of 10 can that machine work at 100% capacity? So some of these machines are light duty. I have a few small machines in the shop that are set at 20% duty cycles. And what happens is we set that welder to 100% flat out. We pull that trigger, that machine will weld for 2 minutes straight, and then it will shut itself off. What this is this is to protect the internal components from heating up. Now, all the components inside of a welding machine, we got a lot of conductors, contactors, things like that. A lot of these are copper. So copper is our general electrical conductor. It's fairly cheap, conducts electricity fairly well. Is it the best? No. The best conductors out there are the precious metals. We're talking gold and silver. But to make all the contacts out of gold in a welding machine, it's going to get quite pricey because there's a lot of contacts. Now, if you crack apart your cell phone, I'm not saying do it, but if you cracked apart your cell phone, in there would be some gold contacts. Gold is one of the best conductors And it also offers the least resistance for electrical conductivity. So resistance is a bad thing. That's what we don't like. Resistance equals heat. Heat is the killer of electronics. So these duty cycles are designed to protect the electronics inside the welding machine. So what happens is you weld for 2 minutes and this machine basically says, all right, I need to cool down. It will shut itself off. It will not start back up, and it'll do that for 8 minutes. That's its rest period. After those 8 minutes have lapsed, you can turn that machine back on and weld for another 2 minutes at 100%. But then you have to take that 8 minutes off again. That machine's got to cool down. Do we ever need to run these machines at 100%? No. Do we? Maybe just to kind of see what it can do, but there's never a time where you should be running a machine at 100% consistently. That machine, if you're doing that, I would recommend upgrading to a bigger machine because you are going to shorten the lifespan of that machine you have. Now, we got some light duty ones in the shops that are 20%. We have some bigger ones that are 60%. So you can hold that trigger for 6 minutes straight, and that machine will just pump out tons of wire, burn it all down. But once again, I don't recommend running a machine at 100%. It is quite hard on it, and it will basically take a little bit of life out of it. It's like running your car at red line all the time. Yes, it can take it if you're doing a bit of spirited driving and you're banging through gears at a little higher RPM, it will take it. But if you're running it at 7,000 RPM, if that's where your red line is consistently all the time, you can expect the life expectancy of your motor to go way down. Same thing with these machines. We don't want to run them at 100%. So gas metal arc welding applications require a constant voltage power source. So we have a continuous voltage is set, and the amperage will fluctuate up and down with the wire speed. So the wire speed actually controls the amperage. So those two are tied together directly. But the voltage is independently set. So we've got a dial on the front of the machine where we set our voltage. All right, now this is a bunch of crazy stuff that you guys don't really need to know a whole lot about that I get into in the 20 level. So we're going to skip past this stuff here. So constant current machines is a constant amperage machine. That's one where you set the amperage, and that would be more like a stick machine. You set the amperage, it would stay there. The voltage will change on a constant current machine. So on a constant voltage, the amperage is going to change. On a constant current, the voltage is going to change. This means that when no work or no arc is being done, the voltage is at a maximum, it's ready to go. And that's what we call open circuit voltage. And when we get into class, we get into the shielded metal arc welding unit, I'll show you this on one of our machines. Our open circuit voltage is generally 71 to 72 volts. And that's sitting there, just waiting to go, waiting to be activated. And then you touch that rod to the plate. Amps are always going to be there, and the voltage will spike up and down. That depends on arc length, how close you keep it, how much resistance is in the arc. And we can kind of do some fun little experiments in class, and I could show you that by keeping a nice close tight arc and opening up a big arc, creating a lot of resistance through the air, stuff like that. It's pretty neat. As you strike the arc, the voltage decreases and amperage increases right up to the point of a dead short where there is no or very little voltage and the amperage is at its maximum. The amperage does not increase enough to change the burn-off rate to help clear the dead short unless you have an arc force dial. So that would be basically sticking a rod to the plate. What happens is, yeah, it's just cranking all that, trying to crank that amp through there and clear it, but it can't. That rod then, basically with all the electricity running through it and steel not being a good conductor, a whole bunch of heat gets made in that rod to the point where that rod will start to glow. It'll glow red and then it'll eventually melt apart, breaking that dead short. It's definitely not good to have a dead short on a machine for a long period of time. You're basically telling that machine to run at 100%. It's not the best way to go about it, but it happens, and I will show demonstrations on that in class and how to avoid that and what to do if it does happen, which it will, because it always does. So yeah, it's a pretty neat little thing here. These graphs don't really, well, don't have to explain those to you at this level, but the upper levels, we'll definitely start talking about those. So constant voltage, constant potential is also what it's called, is what we use for most gas metal arc welding applications. So you set your voltage, and if you set it to 18.1 volts, that's where it stays. Now your amperage is going to fluctuate up and down though. The voltage is still the maximum with no work being done. However, when you dead short, voltage will not drop to zero. So this is the short circuit style welding. So we create that dead short in the short circuit style welding, and that wire touches our puddle. What's going to happen is voltage will not drop, but the amperage will spike out, creating that resistance, that heat. And that heat is going to pull that little droplet of steel off the end of the wire. It's going to clear that dead short. That wire is going to come right down again and touch that puddle. And it's going to happen again and again and again. That is how those work. There's that. We'll go past that. We're going to talk some components about the wire feed controls and the drivers. This is the machines here. We've got a bunch of different ones in the shop. I've got 3-4 different wire feed style machines in here. I've got 3 of the millers, all digital outputs. I've got a 4th miller. It's an analog dials. And then I've got some older machines that are also pretty cool. We'll work with all those. We'll get you familiar with all of them. So important things in that system. Back when I went to the very first slideshow, or the very first slide in the slideshow from Alexander, the patent for the gas metal arc welder in 1924, he had a spindle and a roll of wire. So we still have that spindle and roll of wire. A variable speed electric motor. The variable basically comes from a dial which is called your IPM, or inches per minute. That is telling the machine how fast to send that wire. When you set it, it doesn't change. There are some small little changes that can happen, but it's not like a car accelerator where you press harder and it goes faster. This is when you set it, that's where the wire feed stays at. So we got some control mechanisms. That could be anything from the gun trigger input. There is, in other systems, there are pedals. TIG uses a pedal. TIG can also be a constant voltage with the lift arc, but there's that. So we have a drive roll assembly. So we need to get that wire out the end of the gun. So we have basically the variable speed electric motor. Attached to that motor is the drive roll assembly and accessories. So we feed the wire through these little rollers that press on the wire, basically creating pressure, and then they spin because they're driven by the electric motor, and that pushes that wire out the end of the gun, well, down the hose or down the gun, all the way out the end to our contact tip where it gets energized. And then if we're welding, it's going to weld from there. But this is a roll of wire. So what we have here is a larger roll of wire. I use ones like this in the shop all the time. We use an 035 S6. This one here is, I'm not sure what this one is, but it looks very similar. It'll be an S3 or an S6. This is mild steel welding wire on it. Generally, it's just a couple types that we use. These rolls are 44 pounds. They're quite big. That is so we don't have to change the rolls very often. If I'm running 450 inches a minute of wire, which is a lot of wire, and I'd say got a 5-pound roll on there, I can burn that roll up fairly quick, definitely before the end of the day, probably even in a couple hours. So with these 44-pound rolls, it just keeps us from changing them all the time. So there's less waste, less packaging, less downtime. We want to eliminate downtime as welders. Efficiency is the goal. How do we provide our employers with the best value for dollar? And doing stuff like this is how you do it. So you're not wasting time changing rolls of wire here. I love this picture because it shows the roll of wire, and I hate it at the same time because this gentleman here is going to cut the wire. He's going to change that roll. But when he cuts that wire is going to start to spin off that roll and unwind. It's going to spin to the left because this wire has what's called cast in it. Cast is just the shape the wire takes when it's put on the roll. But if you don't secure the left side there, what's going to happen is you're going to cut it. It's going to spin around, flip around, unroll a whole bunch, and you're going to waste 50, 100 feet of wire, potentially even the whole roll. So always secure that side before you cut the wire. The right side doesn't matter. It's secured by the drive rolls. It's not going anywhere. The left side, got to hold that. And what happens is on these rolls, you guys can see my cursor. I hope you can. Right here, there's a little hole. And what you do is you feed the end of the wire through there, twist it over so it doesn't roll on you, throw it back in a box or a bag, and then you can store it away. This is fine. We'll change the rolls for different reasons. If we have a single machine, we're going to go over to flux core. We need to take this wire off, put the flux core wire on. I helped a student with an exhaust recently. I changed from solid wire to a stainless steel wire, welded the exhaust with the stainless. So it's good to know how to do this. But if you were your own boss and you're working with one of these and you cut this and you let it go and it spins and spins and spins and you waste a whole bunch of wire, that's basically money you're throwing away. We don't want to do that. We want to be as efficient as possible and we want to be as good with our money. So that's why I really like to make sure that students know how to change these correctly and just don't let a whole bunch of wire flap around and turn into a giant bird's nest. So on the other side of those pliers, the right side of the pliers, these are the drive rolls, and this is what holds that wire in place. So generally, I don't know if you guys can see it, but this gentleman's pinching the wire and he's feeding it through this tube here, the guide tube. And then we have a wire roller. It's got a groove in it. That groove is going to be matched to the wire size. They have to match to get it to drive properly. Above it is a tension roller. So this comes down on here. This little section with the numbers on it flips up and holds this down. You can twist this down using these numbers here to set your tension. It's going to press this onto that wire into here. So when this electrical motor fires up, it drives all this right out the end of the gun. Bunch of parts and pieces is pretty simple once you understand how it works, but looking at it for the first time, it can seem quite daunting. So the other end of the gun, this is the end of the gun here. So we got our yellow trigger. This black part here is gonna be the neck of the gun. Up in the neck of the gun, we got a few things going on. We got an insulator in here that insulates the gun from this contact tip this is a gas nozzle, sorry. This is a contact tip right here. This screws into the end of the gun and that gets energized, but we don't want to energize this cup because sometimes we touch the cup against things while we're welding. We don't want an arc to form between the cup and our workpiece. That's definitely a bad thing to have happen. So we insulate the cup from the diffuser and the contact tip. There's a diffuser here. This is it here. It holds the contact tip, but it also has holes in it. There should be 4 holes around it. Those holes are for it's shielding gas. So it pushes out around the end of the contact tip, fills the inside of the nozzle, comes out of the end of the nozzle, shielding your weld, giving you a nice, happy little environment, free of nitrogen, oxygen, CO2, in all those levels that we don't want. Now, CO2 isn't bad for welds. We can use it as a welding gas, but we definitely want to keep that oxygen out of our welds. So drive roll assemblies. We'll talk about some of the components in the system now. They could be 2 rolls, 4 rolls, push or pull, or push and pull. So we're going to get through this part today. I think that's where we're going to end it. We're talking about the guns, and then we're going to stop it there. So 1 roller out of 2, just like that slide I showed you a couple slides back, is going to be the push one. That is fixed to the shaft. It's with gears normally. That motor is going to turn that wheel is going to turn. It's never going to stop unless, something major catastrophic happens. Those electrical motors, tons of torque. That's why Teslas take off on the line so quick and pretty much blow everything out of the water off the line. Instant 100% torque. It's good and it's not good in the welding things. It's great for racing on Teslas, but I don't encourage racing, that's for sure. But in the welding world, what happens is if your wire isn't set up right, it can push a wire out the end of the gun, or it can ball up before the end of the gun and create what's called a bird's nest. That basically is a whole mess of wire wrapped around your drive rolls before it enters the back of the welding gun. This is a big mess. Yeah. So the top one normally has a tensioner. The tensioner should be set tight enough to drive the wire smoothly, but loose enough to let it slip. So what I often do is I'll take my glove and I will hold it over the end of the wire at the end of the gun and I'll pull the trigger. Now, what I want to have happen is I want that wire to come out and push my finger just a little bit. But as I push back on that wire, I want those drive rolls to slip. That's going to stop it from creating a bird's nest on the inside. I recommend doing this with gloves, not your bare finger, because this wire can be sharp when you cut it off. So here we have drive roll pressure adjustment that happens right here. We have our idler right here. There's no motor connected to this one. It's just a bearing. This one, it's got the motor connected to it. And it's secured to a shaft via a keyway and this screw here. I've got a machine in the shop. It's pretty much exactly like this. I'll show you guys when you get back. So sometimes when we're driving wires longer distances and bigger wires, we need more force, right? So what we do is we go from a one-wheel drive to a two-wheel drive, just like we took vehicles from two-wheel drive to four-wheel drive to get us farther. We need to do the same thing with this. So we have one-gear drive roll, two-gear drive rolls. These are tied together on the same motor. They turn at the same time, at the same speed. There's no difference between them whatsoever. Both these idlers are the same. So you'll have a tensioner here and a tensioner here. And this is a much better system for driving longer distances. So a lot of these guns will be up to 15 feet without with just using a push system. The single roller ones, you're only going to see about 6, maybe 8 feet maximum on the single roller drive setups, and generally a smaller wire. Light duty, smaller stuff. As we get double drive rolls, longer distances, heavier wires, bigger stuff. So drive rolls, maybe a V groove. The V groove are going to be the most common. U groove, knurled, or a combination of the above. So basically that just is what type of groove is in those rollers and that the wire fits in. We got an animation coming up to kind of make it more clear to you. The size of the wire the roller is designed for is stamped on the roller. This is what they do because sometimes if we're running a smaller wire, like the stainless wire I was fixing the exhaust with was an 023 wire at 0.023 of an inch, I need to match the drive roll to that. Because if I got a drive roll with a groove in it that's 0.035 of an inch, the wire isn't going to make contact with the drive roll. It's just going to spin, spin, spin. I'm not going to get a wire out of the end of the gun. So I had to take that drive roll out. I had to match it with an 023 drive roll. I put that in place, set the tensioner, welded up the exhaust. It was all good. Then I changed it back yesterday. So what I did is I took that 023 roller out. I took the stainless wire out. I put the 035 roll of wire back in, put the 035 roller back in, readjusted the tension, fed it out the end of the gun. Now it's set up for regular steel again. So drive rollers need to be a minimum of 3/4 of an inch in diameter. This is to keep the wire from curving as it's fed. Basically, if we go smaller than that, it puts what's called cast in the wire. It's a curl we don't want because we want that wire to be straight and we don't want it to be rubbing up at the inside of the liner. The liner is on the inside of the gun, the cable of the gun. And liners are usually made out of spring steel. Some are plastic on the lighter ones, but the spring steel ones are best. If the wire has a bunch of cast in it, it's rubbing against the inside of that liner. And that creates a whole bunch of resistance. That means it's going to have trouble feeding out the end of the gun. This is why I like to keep my guns as straight as possible when I'm welding. So when we do this in class, you'll see when I do a demo, I'm going to unwrap that MIG gun. I'm going to lay it on the floor in one big loop, and then I'm going to weld with it. I'm not going to tie it in small knots because that's going to put a lot of resistance on the wire and make it hard for that wire to come out of the end of the gun consistently. So here are some drive rolls. A drive roll here is knurled. It's got tread on it. It's kind of like a mud bogger. This one here is angled. I've never used angled ones. I've never seen that. But generally there is a third idler bearing here, and that just keeps this pressure and contact against both these. V groove systems. We use these for flux core. I've got some flux core wires, some 045 ones in here that we use. But what we see is a V groove with knurling on it. So it's a combination of the tread and this groove here, and that grips the wire quite nicely and sends it down the line or down the MIG gun. And here we have our U grooves. We got these in the shop. It's probably the most common ones out there. We have these, and when I disassemble a machine, I'll show you guys. They're pretty neat. So this here is a set of U-groove wire rollers. And this set is 035, which is very common. That's the most common wire we use in here. And some of these, you'll see is stamped 035 here. Sometimes what you'll see is they'll stamp 035 on one side and have an 045 stamp on the other. Now, if it's got an 045 stamp on the other side, it means this groove and this groove are going to be different size. So you always want to place it with this number facing you as to what size wire you're working. If you're working with 035, when you put this in the machine, you want this 035 facing you. That means this back groove here is going to be 0.035 of an inch. If you flip it over, you'll see 0.045, and this groove here will be 0.045. Sometimes you have combination rollers. That's just so you have to buy one set. It can do multiple jobs. Sometimes we have dual 035 rollers. So if you don't see an 035 stamped on the other side or an 045, it means both of these grooves are going to be the same size. So there is that. But now we're going to talk about controlling the wire. So we know how to get out the end of the gun now. We know where it comes from. We know generally the process on how it gets out of the gun. But now we're going to talk about the controls that we put in to feed this wire at the rate we want. So the wire feed control panel, that's going to be on our wire feeder. And on some of our units, it's integrated into the face of the machine. And some of our units, it's a wire feeder on top of the machine, a completely separate piece of equipment. So what it has is controls for wire feed speed, which directly influences amperage, because I said those two are tied together, and voltage. Voltage is what we set. These machines are constant voltage. The voltage will never change. Not while welding with gas metal arc welding anyways. The amperage will change a little bit. It will also have a place to plug in the trigger control and a digital or analog readouts for wire speed and voltage, which are optional. Ours are digital on some of our machines. They're quite nice, so you can get very precise, repeatable settings day in and day out. Power source. A lot of these machines, we call them power sources. Especially if we're using a CCCV machine. That means it can do both constant current and constant voltage. It can be used for stick welding and gas metal arc welding, as well as flux core arc welding, possibly even TIG. Well, most do TIG as well. So we talk about voltage and amperage, polarity. Polarity is whether you're running it electrode positive or electrode negative. You also could see it said as DC, which is direct current. So DC SP, which is direct current straight polarity, which is electrode negative, or DC RP, which is reverse polarity, which is electrode positive. So the electrode extension, that's how much wire we have out passing the contact tip. So the distance between our contact tip and our weld. Slope, that's our inductance. Oh, slope is a little bit different than inductance, but they're kind of tied together. Don't really need to worry about that at our level. I'm going to set that for you. They all affect what? Basically, long story short, it's the quality of our welds. So lots of parameters we need to know about while doing this. We could get quite in depth with it, but at the 10 level, there's no need for it. I basically just want to see you guys knowing how to turn the machines on, how to shut them down correctly, how to diagnose a few small problems, and how to operate the machine as far as producing welds. So here, what we're gonna do is we're just gonna check time. And it's 12 o'clock. And we're gonna call that good for today, guys. We're gonna move on tomorrow from the voltage section. I'm just gonna write that down. Voltage. And what I'm gonna do is I'm gonna issue probably a quiz in the upcoming days here. Possibly tomorrow. Tomorrow's Friday. I may offer you guys a quiz tomorrow, or I may just do. No, I get a plan. We're doing a welding demo tomorrow, so I'm going to run you through this machine. I'm going to show you what it's like. I'm going to drag one of our ones out of the back booth, and we'll go through it bit by bit, kind of make more sense of the stuff we talked about today. So we hit you with a lot of stuff. I don't want to go too much farther because you guys are just going to get absolutely lost in it all. So tomorrow I'm going to drag a welding machine out, Fun Fridays. We're going to keep it a little shorter, and that's what's going to happen. So we're going to relate all the stuff we learned about today to that welding machine demo tomorrow. So that is the plan. I'm going to stop sharing my screen here. And if you guys have any questions, now is the time.